Where are you going today?
Good morning. How are you?
I always leave too late. I don't get to talk about it. I got 10 minutes. Slowly start gathering my stuff. And then all of a sudden,
I know. I know.
how long is it?
Yeah. Saturday at night. I can't do Saturday day because I'm going Actually, no. Next week, on Tuesday, I'm going to the conference. So it's going to get here sometime. Yeah, right. I'm free Monday. Yeah, that was such a good thing. What? Oh, this is my last It happened. So for a week. Wow. Not all of us can be smart.
Okay, let's get started. First of all, so we don't have class next Monday, since that's a holiday. So I will see you next Wednesday. Next Wednesday is when the summary for your projects are due. And really all I'm looking for is a page, and maybe 3/4 of a page being just the background of what you know about the hormone and leading into what you're planning to do. And then just like 1/4 of a page on what is your hypothesis and how do you plan to test it. And so what I'll do is I'll take a look especially at that last 1/4 of a page and read it and give you any suggestions about whether I think you're on the right path or not. Yep.
Did you want this in paragraph form or bullet points okay?
Bullet points are fine. So again, this is not graded. This is mostly just to make sure that you're on the right path and working towards it. Okay? Okay, so today I'm going to be talking about calcium and phosphate regulation and the hormonal regulation of it. But just to start, let's talk about how incredibly important calcium and phosphate are in the body. So talking about the roles of calcium in the body, it's incredibly important. So as a structural component, especially with phosphate of our bones and our teeth, it's calcium phosphate that's creating the strength that allows us to stand and to eat. Calcium is also incredibly important for contraction of skeletal and smooth and cardiac muscle. It's the calcium that allows those contractions to take place. A third thing is that calcium is really important for maintenance of membrane potentials in neurons. 4, it has a unique role in the membrane potentials of pacemaker cells in the heart. Number 5, something we should all know about now, it's an incredibly important second messenger for hormonal and neurocrine mechanisms of action. So this is essentially the action of the GQ, hormone receptor. 6 is also something we've been talking about a lot this semester. It has a role in exocytosis of the secretory products from cells. That's what most of the hormones are, secretory products. It's a necessary cofactor for certain enzymes, and it's really important as a component of intracellular matrices, especially the basement membranes that we've talked about. So lots and lots of important things with calcium. Now, approximately 8.5 to 10.5 milligrams per deciliter are floating around in our blood. So it's a fairly high amount. About 50% of that is attached to proteins. Either it's albumins or in other kinds of stuff, and 50% is free, just floating in our plasma. And most of our calcium is attained through the diet. So on the flip side, we have phosphate. And phosphate also is incredibly important. So again, it's really important along with the calcium for the structural components of bones and teeth. It is the calcium phosphate. Second, it's an incredibly important activator of enzymes to its inactive form. This is what our tyrosine kinases are doing, tyrosine kinase receptors. It's adding that phosphate and activating the enzymes. It's also acting as a buffer in blood and other body fluids. So any of you who have worked in a laboratory, especially a molecular or cell laboratory, know that when you make a buffer, you're adding lots of phosphate. Phosphate buffered saline, PBS. Okay? Number 4, it's an essential component for energy storage. This is the ATP. That's that P right there. If you don't have that P, you don't get ATP. You don't get any energy. It's essential component of nucleic acids. There's essential component of phospholipids and cell membranes. It's involved in second messenger formation, right? Cyclic AMP. There's that phosphate again. So we don't get the second messenger if we don't have the phosphate. And it's important and necessary for metabolism of glucose. So just last week we were talking about the metabolism, and what do we get as soon as we bring glucose in? We get glucose 6-phosphate. And that's what starts the glycolytic pathway. So if you don't have phosphate, we're in deep trouble. So phosphate is about 9.3 milligrams per deciliter in the body. And it is approximately 80% of it is floating around as HPO4, and about 20% is floating in the blood as H2PO4. And so a lot of this is then the calcium and the phosphate are actually also bound together. So in regulation, what we see is that the concentration of calcium and the concentration of phosphate, especially HPO4, is equal to some constant. And so the more calcium you have in the plasma, the less phosphate, and vice versa. What that constant is depends upon the physiological state. So, for example, the K increases during puberty, and especially and early in life when you're growing. So children have a higher K than adults do in order to facilitate that growth. Okay? So how is all this regulated? And there are essentially 3 main hormones that are involved in calcium and phosphate regulation. And all 3 of them essentially regulate calcium. So the phosphate is not actually directly regulated by hormones. The phosphate will follow the regulation of the calcium. So if we need to see a difference in the phosphate regulation, we do that by regulating the amount of calcium. And we use this relationship to regulate the phosphate. All right, so the first hormone we need to talk about is parathyroid hormone, or PTH. And PTH is released by the parathyroid glands. Okay? So here's a slice through the thyroid gland. All of these are your follicles that are secreting T4 and T3. But embedded inside all of those inside that tissue is the parathyroid gland. And so this is the parathyroid gland. And it is secreting PTH. Something like 99% of the cells, almost all the cells inside the parathyroid gland are secreting PTH, parathyroid hormone. So parathyroid hormone, PTH, is the primary hypercalcemic hormone. So it is involved in getting an increase in calcium. And so it is the release is stimulated by low calcium levels. So it's actually one of the unique hormones in the body that's actually stimulated by a decrease in calcium. Most hormones are released by an increase in calcium. PTH is secreted by a decrease in calcium. The parathyroid hormone is about an 84 amino acid peptide. And with a half-life of about 1 to 2 minutes. However, biological half-life is about 20 minutes. So what does that mean? Difference in the half-life. So we draw a graph, and this is time, and this is the concentration of PTH. And we see a curve like this for its half-life, but a curve like this for the biological half-life. So why is this difference occurring? Yep. Great. So thinking about a carrier protein. Turns out that that is not explaining why we're seeing this. So that is the classic way in which carrier proteins work. But in this case, it's not a carrier protein that's doing it. So how else could we get a difference between the half-life and a biological half-life? Yep.
Is it at a different pH in the blood or in the biological system?
Good question. Probably not. It's not a difference in pH.
Is there like a ion or something that's attaching to it and creating a conformational difference that stabilizes the shape so it can stay around longer?
Fantastic idea, but no. Yeah.
Maybe it aggregates so that the size is bigger, so that it's degraded slower.
Okay. So we could test that. How?
One of the lab techniques.
No, but we could look at what the degradation rate is, right? And it turns out the degradation rate is not any different. Yeah?
Is it binding to receptors and it's not being degraded?
Great idea. How could we test that? Maybe we could look and see if it's bound to its receptor, does it stick around? And not any more than any other hormone. Yeah?
We don't know.
We do know. Good guess. But think about it. You have this hormone that's being degraded and yet still has biological activity. How could that work? Yeah.
As it's being degraded, do those, like, the way that it's being degraded also have biological activity?
I think your answer is correct. So the answer is yes. So how could that work? Yeah?
Only a very small portion of the
34 amino acids actually is relevant. So even when it gets degraded, if you keep those together, they still work.
And that's exactly how it works. So I think you were almost there. So yes, it's an 84 amino acid peptide, but only 34 amino acids are needed. So the hormone gets released and it starts getting chopped up by your peptidases in the blood. But that's okay, because a lot of the fragments that end up coming out of being chopped up still have biological activity. And so you end up with a situation where you have a difference in the half-life of the peptide and its biological half-life. And there aren't, I don't know of any other hormones in which this is true. Yes?
So, do the amino acids, do like the extra amino acids still have other functions, or are they kind of designed so that the hormone has a longer biological half-life?
As far as I know, nobody's found any biological activity for those other amino acids. So they may be important folding, and then, but then once it's folded, it's okay, and they just don't get degraded during post-translational processing.
So when they're chopped up, like, does the protein not change?
I actually don't know. Yeah. Yep.
Yeah, I have like a similar question is like, so in its original form, is it like more functional or less functional?
Totally equivalent, because you only need those 34 amino acids. So these are the only things that are needed. And so all of this could be degraded. But you're getting the same activity from this as you get from this.
But what if by accident like the peptidases affect the 34?
Then you'd lose activity.
So it's a random.
And that's why you're getting degradation even here. And it's just random where that peptidase is going to start working.
Oh, I see.
Yeah.
Is there a specific 34 amino acids that are needed?
Yep.
And are those more internal to the peptide?
I think the last time I looked, I think they're at the end terminus. Was it the C terminus of the peptide? Okay, so what we get is a longer half-life than we would normally get. But parathyroid hormone is then released and is and what you get then is all of the parathyroid hormone being released and going to its target cells. Okay? So this is the hormone that's going to be increasing the amount of calcium in the blood and mobilizing our calcium stores. On the flip side, our second hormone is calcitonin. And calcitonin, CT, is the primary hypocalcemic hormone. And so this is stimulated by increases in calcium levels. So as the calcium levels increase in the blood, you get the release of calcitonin. And calcitonin is being released by also from the thyroid, but inside and surrounding all of these follicles in the thyroid are what are called these C cells. And they're secreting calcitonin. So many of you probably don't remember, but when I put up the figure a long time ago, looking at the thyroid gland, there were these C cells in the thyroid gland, and that's what these are. They're now secreting the calcitonin. So everything is really happening in the thyroid gland, but different from the production of T4 and T3. Okay, so what is calcitonin doing? So calcitonin is about a 32 amino acid peptide, it has a little bit longer half-life. It's a half-life of about 5 minutes. And the entire peptide is different from the parathyroid hormone. The entire amino acid sequence is required for activity. Okay, so we've got the parathyroid hormone, we've got the calcitonin. The third hormone in this group is going to be 125-DHC. All right, so here's a synthetic pathway of 125-DHC. It all starts from cholesterol. And so this is why, even at the beginning of the year, I mentioned that when we're talking about the 5 different classes of steroids, that one of them is a sixth is often called vitamin D. And that's because it starts off with the same ring structure as the other steroids, because it's also coming from cholesterol. And so this is a really cool system. Because we need to break the 2 of these rings in order to form cholecalciferol, which is also known as vitamin D. And that breaking of these ring structures can take place through an isomerization step, but that is very, very slow and not sufficient to keep enough vitamin D in the body. And so the cholesterol goes to the skin, and the ultraviolet light will then break these bonds and allow us to produce vitamin D. So vitamin D is produced in the skin. Once it gets produced in the skin, it travels through the blood to the liver. And at the liver, that adds in hydroxylase and creates 25-hydroxycholecalciferol, which I have to practice every year. Essentially, I always thought it was 25-HC. Okay? And 25-HC is an intermediate. So the liver converts it to 25-HC, then releases it back into the bloodstream, and 25-HC then travels to the kidney. And the kidney converts it into 125-DHC, or 125-dihydroxycholecalciferol. And this is our active hormone. And then the kidney then can also convert it into 2 different inactive forms. So this is inactive, and this one is inactive. Okay? Yes?
Is it random whether it becomes activated or inactivated, or?
Well, part of it is it can get deactivated directly, and also it gets deactivated in the kidney through another enzyme.
So
Okay.
proportionally more of it gets inactivated?
Yeah, I don't know what the proportions are, but the primary product here is 125-DHC. Okay? So this, by the way, this incredibly important thing, the effect that's taking place in the skin, has been proposed as one of the reasons why we get the evolution of light skins. And so in the current theories and hypotheses of the evolution of humans, and the migration of humans, that we had Homo sapiens moving out of Africa initially, had to have been all dark skinned, because you have to protect your skin from the ionizing effects of solar radiation. But then as you move up into the northern climates, you start to lose a lot of the sunlight. And when you lose the sunlight, you're going to lose this conversion into vitamin D. And so you're going to start becoming vitamin D deficient. And so one of the ways to avoid that is to stop producing as much melanin in the skin. And so it's still true that a lot of Africans who move into the far north have problems with vitamin D deficiency problems. Now, we don't have any problems with vitamin D deficiency anymore, primarily because of why? Milk. We fortify our milk. So when you go to the store and you buy milk, you're getting vitamin D fortified milk. So we just put it in our milk. Okay? So, but that's one of the hypotheses for why Caucasians lost the production of melanin. Okay, so now we have our three main players. We have the parathyroid hormone, we have the calcitonin, and we have the 125-DHC. They're being produced, and now how do they regulate calcium? Yes?
So parathyroid hormone increases calcium, calcitonin decreases. What is 125?
We're going to get there. There we go. All right. So what we have is all this calcium that's coming in. One of the biggest things that causes a major change in our calcium levels is eating a meal. So we have a dietary intake in a general diet of somewhere between 900 and 1,000 milligrams of calcium a day. And that comes into the intestines, and we need to get it out of the intestines. So the major flux of calcium out of the intestines is regulated by 125-DHC. So that is what is, the 125-DHC is going to the cells lining the intestine and causing them to produce a calcium transporter. It transports it out of the intestine and into the blood. In addition to that, parathyroid hormone stimulates the production of 125-DHC. So parathyroid hormone has an indirect effect also on transporting the calcium into the body. So now what we have in the body, in these extracellular fluids, we now have high levels of calcium. So what gets stimulated with high levels of calcium? Calcitonin. And so calcitonin is going to start shifting the calcium into the bone. So this is calcitonin. And it does it in two different areas. So we have the what's called a rapidly exchangeable bone mineral. So this is for short-term storage. And we also have this stable bone mineral. And this is going to be for long-term storage. So now that we've got our calcium into our storage sites, we're going to start seeing the change in this calcium flux. So we're going to lose a bunch of our calcium directly out. We're just simply not going to secrete it. But we've removed all the calcium, and now we're going to start to see lower levels of calcium in the body. And so at that point, we're going to secrete parathyroid hormone. And parathyroid hormone is going to bring the calcium back out from the bones, and it's also going to help save calcium from being released and lost in the kidney. So we have parathyroid hormone working here, and we have parathyroid working here. Yep.
Could you explain what parathyroid hormone does with the kidney?
Kidney, we're going to get into this more in a minute. But what it's doing is helping save. Because remember, calcium is just an ion. So if you remember, what's happening with the kidney is it's all going into the glomerular filtrate. If we don't want to lose what is in basically our blood plasma that gets filtrated through the glomerulus, we have to actively save it. That's why we have to actively save the glucose that we want. We have to actively save the water that we want. We also have to actively save the calcium that we want. And so what the parathyroid hormone is doing is acting in the kidney to bring that calcium back out. And 125-DHC is acting permissively to also allow that to happen as well. Yes?
Does the DHC only act permissibly at the kidney?
Yes.
Okay.
Yep.
So could you explain the difference in the role between short-term and long-term storage areas? Is PTH working differently in both?
Yep, and I'm going to talk about that in just a second. Okay? Because how this works at the bone is really fascinating. Any other questions before I move on? All right. So what's actually going on in the bone? So there's essentially 3 different kinds of bone cells. There's the osteoblasts, and they build bone. The osteoclasts, which destroy bone, and the osteocytes, which are mature bone. So these are the these are cells. So the osteocytes have produced so much calcium phosphate that they're completely surrounded by calcium phosphate, and they exist in these little pockets inside the bone with basically the little bit of channels between them to allow nutrients and things from the blood to continue to feed them. So these osteocytes are forming this mature bone. That's this long-term storage site. Okay? But at those margins where bone is being built, you have the osteoblasts, which are in the process of building bone, and the osteoclasts, which are destroying bone. And that's that short-term storage site, because there's always this balance of the osteoblast and osteoclast activity. So how do we so osteoblasts are these cells that just simply are putting in bone matrix. So they're creating the calcium phosphate and excreting it into the extracellular matrix to create bone. How that works is still not well understood. Okay? But what we do know is the osteoblasts, when they get a signal from parathyroid hormone and 125-DHC, they bind to their receptors and they cause the production of some sort of an osteoclast differentiation factor. It's called a factor because we still don't know exactly what it is. But we do know that the osteoblast produces something that causes this osteoclast progenitor, and these come from macrophages or early T cells that are involved in the immune system. And they interact with the osteoblast and get converted into a mononuclear osteoclast. And then these then become mature osteoclasts at the interface of the bone. Okay? So the osteoblasts are making osteoclasts, but only when they get the signal from parathyroid hormone and the 125-DHC. Okay? So what is happening, this is the osteoclast. And what the osteoclast is doing is it is converting with carbonic anhydrase, water and carbon dioxide into a carbonic anhydrase, which is then through an ATPase is secreting acid into the extracellular space. And this is this is outside the cell, and this is starting to break down the calcium phosphate. And it's activating especially these lysosomal enzymes, which are also being secreted by the osteoclast. And this then is mobilizing the calcium. And the calcium then flows into the cell, and then we have a calcium channel where the calcium flows out. Okay, so we have all this bone matrix, and these osteoclasts are basically landing on the bone, secreting all of this acid and all of these lysozymes, which are then breaking up that bone matrix and releasing the calcium, and the calcium's flowing out. Now remember, we're also, because it's calcium phosphate, we're also getting the phosphate released as well. But all of this is being regulated by the flow of the calcium. So what happens? We have PTH, which is stimulating an increase in the number of osteoclasts. And this then stimulates the increase in calcium release. So the PTH, the parathyroid hormone, is actually working in an indirect fashion to stimulate the release of the calcium, simply by increasing the number of osteoclasts that are functioning. Okay? Yeah?
Just to clarify, so PTH is increasing the number of osteoclasts, which is therefore increasing the number of calcium release, or?
That's being broke down and released into the blood.
Okay.
So if we come back to this figure, right? We're having this parathyroid hormone, talking about the calcium being released from here, is primarily due to an increase in the number of osteoclasts. All right. And now, what does calcitonin do? The calcitonin here is binding to its receptors on the osteoclast. And so that then prevents this activation. So it decreases the amount of acid being released, so it decreases the activation of these lysosomes and thereby decreases the outflow of calcium. So calcitonin is then inhibiting the action of the osteoclasts. So we come back again to this figure. I'm showing that the calcium is going into the bone by calcitonin, but that's not actually completely accurate, because the calcitonin is not actually stimulating the production of new bone. It's inhibiting the destruction of bone. And that then allows the osteoblast to continue to build. Yeah?
Does calcitonin decrease acid production or decrease acid transportation?
That's a good question. I don't know if they know.
Oh.
Yes?
For calcitonin to work well, don't we need to make the osteoclasts in the first place?
Oh, but what if there's no osteoclast? Then we're still going to get osteoblasts using the calcium and building bone.
Oh, okay.
Because it's the osteoblasts that are doing this. Okay? So these osteoblasts are building the bone. The difference is that the calcitonin is not stimulating the osteoblast. It's just inhibiting the osteoclasts. So if there aren't any osteoclasts around, or they're not functioning, then you're just going to get activity of the osteoblasts and the building of bone. Yeah?
So the osteoblasts are making the bone, but they're also releasing the osteoclasts.
Yes, but only when they get
Okay.
the stimulation from the parathyroid hormone. Yep.
So is this mostly regulated based on dietary intake of calcium? So,
Mostly, yes.
and if you have a higher acid diet than not, would that change the amount of acid that would necessarily be present in the bone as well, or is that just a different type of acid that's present?
No, and it's only the local production of this acid. So you're not going to get acid coming out of your intestines and going to your bone and stimulating this. So there's too many steps between there that the body will stop that.
I just wasn't sure if it would change how the PTH would be, considering that's based on how little calcium would be present. So I don't know if that increased then this process to be increasing calcium in the blood then.
I don't think so.
No?
Yeah. Yep.
So in the other diagram, you said that calcitonin allows for the movement of excess calcium stores to the bone, but it doesn't actually stimulate bone production.
Correct.
So how do you get rid of those excess calcium stores?
So the calcium stores are being moved into the bone by the osteoblasts. And what the calcitonin doing is shutting down the destruction. So you have this process here of building and destroying is always in a balance inside the bone. And so if we inhibit the destruction of bone, then the consequence is going to be an increase in the production of bone. And that's how the calcitonin is working. Not by stimulating the production of bone, but by inhibiting the destruction of the bone. Yeah.
Did you say that calcitonin inhibits or decreases calcium output
From these cells. Yep.
from the osteoclast?
From the osteoclast.
And
So it's
that's
inhibiting all of this process. So what you're going to end up with is no outflow of calcium because it's not being produced out here. What we're doing is just think about you don't need to go too deep into this because there's, the number of papers that have been written about how calcitonin works are huge. The important thing here is that the calcitonin is basically inhibiting the activity of the osteoclast. So the osteoclast is not working when it's under the influence of calcitonin. Is there another question over here? Also, okay. Yeah.
How does DHC regulate it?
In terms of the bone, it's also part of this step here, both PTH and 125-DHC. In terms of,
Is it permissive or they both need it at the same time?
they both seem to be needed at the bone. Okay? Oh, by the way, one other thing that happens is that there are things that can stimulate osteoblast activity. And one of them turns out to be estradiol. So estradiol can stimulate the production and the activity of osteoblasts. This is why at menopause, when women start to lose the amount of estrogen that are in the body, you start to see a reduction in the osteoblast activity, and why women are about 8 times more likely to suffer from osteoporosis than men, because of the loss all of a sudden of the estrogen that's stimulating these osteoblasts. Yep.
If osteoclasts are won't they eventually die?
No, they're always there. The calcitonin just turns them off. It doesn't kill them.
Okay, I'm just wondering, so if we're making osteoclasts from the progenitors, how do we balance the number of osteoclasts we have, or do they just keep on increasing?
We do that by regulating the amount of PTH and 125-DHC, because if these hormones are not present because we have sufficient calcium, then the osteoblast is not converting the progenitors into an osteoblast. Okay? All right. So now let's look at the role of the 125-DHC in all this as well. All right, so what we have is sunlight creating our vitamin D3. It's moving in the blood to the liver, where we get the production of 25-HC. 25-HC then goes through the blood to the kidney, where we get the production of 125-DHC. This production is also stimulated by parathyroid hormone. Okay, so this is a major stimulant also of the production of 125-DHC. Once 125-DHT is released, it has 3 primary roles. Okay? Number 1 is it goes to the gut and stimulates the uptake of the calcium from the gut. So we have uptake. The second thing it's doing is going to the bone and stimulating the release of calcium from osteoclasts. Again, this is indirect, much like the effect of parathyroid hormone, by increasing the number of osteoclasts. And then the third thing it does is it goes to the kidney and essentially helps in a permissive effect on PTH, the saving of calcium from the kidney. And then we have negative feedback. So we have the increase in calcium and the phosphate. This increase in phosphate feeds directly back to the kidney and inhibits the action of conversion of 25HC into 125DHC. So that's one negative feedback loop. And the increase in calcium is now going to inhibit the parathyroid gland, and so we're going to get a decrease in PTH release, and this will then inhibit this pathway so that we don't get PTH stimulating the production of 125-DHC. Okay, so those are negative feedback loops. So if we do it in a little bit different way, we can have PTH is stimulating production of 125-DHC, which is then going to create an increase in calcium. And then the calcium will feed back and inhibit PTH, which will then result in a decrease in the production of 125-DHC. It's the same thing I wrote here, just in a slightly different way. Okay? Yes?
Sorry, so PTH is needed to make
Yep, it's right here. PTH stimulates this production from 25HC to 125DHC.
Oh, I see. So both the increase of phosphate and calcium will, in different ways, will decrease the 125 DHC.
Yep.
Oh.
So two pathways for negative feedback. Yep.
Where's the PO4 coming from?
Calcium phosphate,
Calcium. Okay.
right? So you're breaking down that bone.
Oh.
Okay? All right. Here's another way of thinking about it. Just different ways. So we have our diet. We're eating 1,000 milligrams per day. About 640 of that is not being absorbed. So we're only absorbing about 360 milligrams per day, and that absorption is being regulated by 125-DHC. Once it gets into the blood, our calcitonin is going to shift it so that it allows it to be stored inside the bone. We also are going to get all of this, about 170 milligrams per day, being lost into the kidney. But we have plenty of it coming in from the intestines at this point, so we don't need to save it, so we're going to lose it in our urine. Then we stop this process, and now the PTH needs to mobilize it again. So now the PTH is bringing the calcium from the bone back into the blood by activating or increasing the number of osteoclasts, and it's working directly at the kidney, both by stimulating 125-DHC production, which is then moving over here, and also helping save a lot of that calcium that went into the kidney. Again, to increase the amount of blood calcium. All right? So what we end up with, if we just look at the serum levels of these two hormones. So this is the open circles are the serum levels of PTH, the closed circles are serum levels of calcitonin, and this is the serum calcium levels. So as the calcium levels go up, we start to see this increase in calcitonin, and then as they start to fall, we see a decrease in calcitonin, And then we start to see, as it continues to fall, we start to see the increase in parathyroid hormone. And so the balance of these two hormones is going to create a balance in calcium of approximately 9.3 milligrams per deciliter. And so the whole idea is that we're going to try to regulate it to there. So if we looked at the actual amount of calcium in the blood over time, here's our 9.3. We're going to see as the calcium, so you have a meal, as the calcium levels start to increase, this is going to be when calcitonin is high. We'll then get rid of it, it will start to drop below, and now we have our parathyroid hormone working. And so we're going to see this kind of rhythm, this oscillation of calcium levels throughout the day as we eat and as we clear it. All right? Yes?
And then the 125 DHC would be active when the thyroid hormone's active?
Yep.
Okay.
All right, yes?
Is 125 DHC also like broken down with no parathyroid hormones?
Yes. All right, so one last way of thinking about this. This is the figure. I showed this figure because this is the figure that when I was learning this finally made sense to me. And it's partially wrong. But anyhow, I'll show you how. So, we have an increase in calcium. The increase in calcium is detected by the parathyroid gland. It then secretes PTH, parathyroid hormone.
Is that an increase or a decrease?
Sorry, decrease in calcium. Sorry. It's decrease in calcium. Okay? Parathyroid hormone releases parathyroid hormone, PTH. It then has three effects. It's going to the kidney, where you're getting calcium reabsorbed. It's going to the bone, where you're getting calcium released. And it's going to the GI tract, which is actually working to increase. So this is where it's wrong. It doesn't do that. It increases vitamin D, and the vitamin D affects the GI tract, and you get the calcium absorbed from the GI tract. The whole result of this process is you're going to get an increase in calcium. That increase in calcium then becomes the input to this process, where the increase in calcium also gets detected by the thyroid gland, but these are the C cells, not the parathyroid gland, but the C cells of the thyroid gland. And that's going to secrete calcitonin. Calcitonin is going to allow the bone to incorporate the calcium, so you're going to be left with the decrease in calcium. And then this feeds back here, where you get the decrease in calcium, now stimulating the parathyroid gland to create PTH, etc., etc., etc. Okay? All right. Let's see how good you're thinking. Data. All right. This is your detection limit of plasma calcitonin. So this is measuring calcitonin levels. This is a normal woman. She has, and this is the levels of calcitonin. This is the mean, and these are essentially the spread of the amount of calcitonin. When that woman gets pregnant, she has a massive increase in the amount of calcitonin in her body. Why? Think about that. Yeah?
Because you have to, now the parasite, as you like to call it, needs to produce bone, so it's probably taking the bone that, or the calcium that's in the mother and bringing it through the bloodstream into the fetus so that they can produce their own bone.
Okay, but if what you're trying to do is mobilize bone in order to give it to to the
Why would it
fetus,
increase calcitonin?
then
So
yeah,
that
why are you
needs
increasing
the
calcitonin?
feedback, though, so you can increase the PTH.
Yeah, okay. So how do you test that?
Check the levels of calcium that's in the blood, because if you increase the PTH, there should be an increased level of
Okay.
calcium in the bloodstream.
Why don't we look at PTH?
You could look at PTH.
PTH levels are normal. Yeah.
You just support the extra weight from carrying the fetus, and you need stronger bones to support.
Interesting idea. That might be part of it, but that's not what people are normally thinking about this. Yeah?
The fetus is trying to grow bone, so it makes sense to have the calcitonin that's inhibiting the osteoclast that would destroy the growing bone. So that could be the explanation for having these high levels, so that way you're not destroying bones in the fetus as they're trying to grow.
Okay, but that would be inside the fetus. Great. Doesn't look like calcitonin goes over the placental area. So this is actually probably affecting mom, not the fetus. Yeah?
Does it have to do with like mom is preparing for lactation to feed the baby?
Okay. That's the next thing, the lactating woman. That's not yet. This is only during pregnancy. Yeah?
Is there more like estrogen in the body and that would increase hormone?
Okay, so what is estrogen doing? It's increasing osteoblast function. Okay, so that's going to be exactly the same thing that calcitonin is doing. So why do we have both of them increasing? That makes even less sense. You guys want a hint? The hint is HCG. People remember what HCG is? Right? Human chorionic gonadotropin. So this was a hormone produced by the fetus, chorionic, that is hijacking mom's hypothalamus so that they continue to produce estrogen, even though negative feedback has shut it all down. So there's your hint. So why does mom have such high levels of calcitonin? Yeah?
Well, doesn't the HCG, along with it, don't you get chorionic somatomammotropin? And so that's going, that's being produced by the fetal tissue, and it's stimulating the growth of the mammary tissue and increasing the production of milk in mom?
Yep.
And so are you seeing increased calcium because you're getting increased production of milk and mom, and that's why you're seeing increased levels of calcitonin?
Well, but if we want to increase the level of calcium in the blood, why are we secreting calcitonin? We should have very low levels of calcitonin and high levels of PTH. Right? Yeah?
Because the fetus want mom to store more calcium so that it becomes time for production of levels in excess. High levels of calcium that are available for PTH to break down.
Yeah, you're getting closer, but you're still focused on lactation. This has nothing to do with lactation yet. Yeah?
Isn't calcium used for contraction?
Yeah, we're a long ways from parturition, birth. This is growing throughout the 9 months. These calcitonin levels are going to be high. It's not just at the end. Yeah?
Is the fetal frequently, which is
Nope.
why you.
All right, hint number 2. The fetus is a parasite. What does the fetus want? Fetus wants to grow, right? It wants to grow big. It wants calcium. It wants lots of calcium. Is mom going to give it lots of calcium? No. So what does the fetus do? The fetus secretes PTHRP, parathyroid hormone related peptide, which acts just like PTH. So this is the fetus, the chorion of the placenta. Fetal tissue is secreting a new hormone, PTHRP, that's going into mom to stimulate the destruction of her bones and her teeth in order to provide the calcium that it wants. And mom's body says, oh boy, wait a second. I need to protect my bones and my teeth. And you see this massive increase in calcitonin trying to stop this process. Yeah?
So where does the fetus get the calcium it needs eventually?
From mom, from mom's teeth and bones.
So, okay, so it's like, even though mom's still trying to protect herself, the fetus still gets...
Oh yeah. So, small personal story. My mother says, I wasn't around for this, but she says that she never had a cavity in her life until she was pregnant with me. And at the end of her pregnancy with me, she went to the dentist and ended up having something like 15 or 20 cavities that had to be filled. Why? Because I apparently sucked her calcium dry. I ripped it out of her teeth and out of her bones in order to take it. And every single one of us did that to our moms. You should go home after this class and say, thank you for giving me the calcium out of your teeth and your bones, because we ripped it right out. And we did not ask permission. Okay, so this is a serious problem. So there's a lot of osteoporosis, there's a lot of teeth decay that happens in pregnant women because of this parathyroid hormone related peptide that's produced by the fetus that goes and tries to steal the calcium from mom. You guys are never going to think about pregnancy the same way ever again. Yeah.
So how much extra calcium should the mother be intaking so then that doesn't end up happening? Because obviously the levels that you said are like 1,000 or so is how much you normally intake, and you have excess, and obviously the fetus is sucking all of that dry, even the excess that you're not taking up.
I do not know the answer to that, but my guess is that somebody does know that. So my guess is that OBs are now telling pregnant women how much extra calcium to take. I know when my wife was pregnant with our kids, she was prescribed calcium, extra calcium. Now, how much you need, I don't know. But yes, that can help solve this problem. Okay, so then once the child is born, now we start to lactate, and the calcitonin levels are still high. And this is actually slightly different, because now we do want the extra calcium in the blood so we can give it through the milk. And now mom starts to produce PTHRP as well. That goes to her mammary tissues, not to the but to the bones, that allows the extra calcium to be used by the milk-producing cells that are being stimulated by prolactin. Okay, so again, mom has increased the amount of calcitonin because she's also increased the amount of PTHRP that's being produced. All right. So just to finish up a little bit here, just talking about some of the problems associated with calcium regulation. There aren't a whole lot of calcium-related diseases. And why is that? Because think about all those things that I pointed out that calcium and phosphate are important for. If you're not regulating those pretty well, it's lethal. Okay? So there's not a whole lot of problems that you can face. One of the things that can happen, though, is you get osteoporosis. So this is a densitometer scan through normal, healthy bone, and this is through a bone in which there has been a significant amount of osteoporosis. Okay? But it's not just the this osteoporosis, but the parathyroid hormone and calcitonin are working together to also remodel bone. One of the things that really surprised me as I started to learn all this stuff myself is that bone is living tissue. We think about it being sort of quasi-dead, but it's not. And that we can actually completely remodel our own bone tissue depending upon need. So, for example, weight-bearing tissues. I'll have to look up the percentage here. 28 to 35% more dense bone in a tennis player's racket arm versus their non-racket arm. 25 to 35% denser bone in that racket arm that they're using. That huge amount of activity and swinging that they do remodels the bone. Okay? One of the most fascinating papers I ever read was actually in an anthropology journal in which they were excavating a village somewhere in the Middle East, and they were pulling out these bones, and there were mostly just leg bones and body bones. They weren't finding many hip bones or skulls or anything like that, but they knew that most of the bones they were pulling up were women. And it was really fascinating how they decided that these were women, because they were looking at their, not the femur, the tibia, and they look at the tibia, and they had big calcified bumps right here, right underneath the knees of these individuals. And what they just thought is that these are the women who spent their entire lives kneeling on the ground in order to grind the grain. And so all that kneeling, day after day after day, hardened that bone and created a large, not a bone spur, but a big area of calcified bone. So the bone is getting remodeled all the time. There's a problem with the flip side of this, not having bone weights. Does anybody know where this is a serious problem of losing weight bearing, and so you lose bone mass? Astronauts. Absolutely. Astronauts lose approximately 1% of their skeletal bone per month that they're in outer space. And interestingly enough, they never get it back. One of the fascinating things about, if you go back and you look at all of these old pictures of astronauts arriving from outer space, and they interview all of these astronauts after they come back, and they're always sitting down. And the reason is that most of them couldn't stand up. And that's why people out at the International Space Station are required to spend a couple of hours every day on a treadmill, trying to get, and a treadmill's great for the muscles, but it doesn't really help the bone, because you still are not bearing any weight on those bones. And so the NASA doctors are really trying to figure out how can we save bone from being destroyed simply because we're in a weightless situation. So I was at a meeting a number of years ago talking to a bunch of NASA doctors, and one of the things that they were talking about is how the major goal of NASA right now is to get to Mars. And so I think several presidents, including currently Trump, have said that one of the goals of NASA should be to get humans to Mars. And this NASA doctor said, we can't do it. Says, at least with the technology we have right now, we simply can't do it. We think we can get them there. We certainly cannot get them home. He said, because number one, we can't get enough food into these spaceships to last the time it's going to take them to get there. which is why there's been a significant amount of research on hibernation paid for by NASA to figure out how we can get our metabolisms low enough so that we have less food requirements. He says we can't figure out how to keep their bones stiff so that by the time they're gone for this, maybe 2.5 years in space before they get to Mars, they're not going to be able to do anything once they get there because they won't be able to land. Won't be able to do anything. They won't have the muscle mass or the bone structure to actually do anything. So there's a huge number of these issues that, at their root are caused by endocrinology that the NASA doctors are trying to figure out and how to do with their astronauts. Okay, there is one disease that is caused not necessarily by a lack of calcium per se, but a lack of vitamin D. And that's called rickets. And here's a couple of pictures of kids with rickets. And these are individuals that aren't getting enough vitamin D. So you tend to get this really knock-kneed situation, or you get a lot of bow-leggedness. And so I did find this one picture, which is really amazing. So this was a photograph of a kid taken at the end of the late 1800s in London, and is suffering from rickets. And you could see the bowing of these legs. And this was a rather common illness in London in the late 1800s because of all the smog that was preventing sunlight from getting down, especially into the slum areas. So you get a lot of rickets. However, this picture always reminds me of this other story that's kind of funny. So I had a friend who adopted a kid from overseas, and when he arrived, he was about 14, 16 months, somewhere in there. So he was already learned to walk, and as he was running around the house, his legs were bowed, and I and a physician who was there said, you need to get this kid checked out. It's a good possibility he might have rickets. And so they totally freaked out, these poor parents. And they took this kid in to get checked out. And the next week they called me up and said, well, as it turns out, the kid does not have rickets. What happened is that he was learning to walk, and in this overseas orphanage, he was using cloth diapers, not the plastic diapers that we use in this country. And the cloth diapers created a huge amount of space, and so this kid was learning to walk around the cloth diapers. It looked like it had bowed legs. But as soon as they took him off, stopped using cloth diapers and started using the plastic diapers, he didn't have to walk around the diaper, and his legs straightened right up, no problem. Yeah.
I've actually heard that being a problem with a lot of the new baby carriers that people have because they're spreading their hips out too wide, and babies are having issues with stuff like that. So you have to watch when people order those special things, holding the babies in a certain way because it's spreading their hips out and they're not supposed to be that way.
Interesting.
Mm-hmm.
So, and this brings me to the last thing I wanted to talk about today, which I just found incredible. Here's a picture. This is actually hanging in a museum of this picture of this mother and this kid from sometime around the 1500s. This was the members of the Medici family. People remember from their history who the Medicis were? This big Italian family that basically regulated, they were merchants, and they regulated shipping throughout the world for about 300 or 400 years. At least one of the Medicis became Pope at one point. Big family, the important family, but one of the things that became very popular at about that time is to be very pale, because only, you tan when you're out in the sun, and the only people who are out in the sun tanning are the laborers. So the whiter you were, the more prestigious it was, because it showed that you weren't actually out in the sun working. And so a lot of the women, in fact, if you take a look at her dress, they wore incredibly covering dresses that covered all of their skin, right up to their wrists, down to the ankles, and then they put on gloves. She's wearing gloves here, and then they not only that, but they'd use white makeup all over their faces, and they were not getting any sunlight, and they were getting serious vitamin D deficiencies. Now, it's not such a big problem in mom. She's already well grown, but it looks like this kid might have suffered from something, and he's holding on to mom's hand. Well, they recently found his skeleton in the crypt in the church in Italy where he was buried. He died at age 5 or 6. And believe it or not, you take a look at the bones. Here is his femur. Here's his tibia. They are bowed. These kids suffered from rickets. And also the skull. They have a classic increase in the size of the skull that occurs because of rickets. And so this this sociological idea that we're not going to show that we can tan had a negative impact on the kids that were being born in these families. Okay, so have a good long weekend. I will see you on Wednesday.